that
this?
counts as notation.
All right.
And it's the word.
Mr. Alexander.
Not right now.
But this is for going into it. How is this in logarithmic form? Okay.
Let me teach. 'Cause I need that.
Okay. So today we're working with, I can differentiate natural logarithms and E. Okay. First of all, refresher on some things because I know we probably need it. Okay. E.
Equals MC squared.
Is about 2.718. 28. 1.846. Okay. You don't need to have that memorized by any means. It's probably good to know it's a little bit less than 3, but remember the number E, okay, is about 2.7. E is the base of the natural logarithm. E is the base of the natural logarithm. For instance, if you see this, ln of x equals 4, it's like there's a little e right there. E is the base on the natural logarithm. And if you were to change forms from logarithmic to exponential,
E to the fourth equals
wait,
X.
e to the fourth is equal to x. The little base raised to the number on the other side is equal to x. Okay? E to the fourth would equal x. Okay? That's changing forms. This is what you were talking about.
Right.
Logarithmic form, exponential form. Okay? Because when you see ln of x, all right, you're basically saying, okay, well, what e raised to what power is equivalent to this value? Or what exponent would e need to equal that value?
So we
Okay.
don't have to change forms and then do like chain rule or something?
The changing of forms really helps you understand the proofs.
Yeah.
Yeah, I heard the resonating of lead.
The noise?
Yeah.
Yeah.
I don't like it.
There's a high pitched noise. It's someone's lead.
But I wanted to refresh your memory on that. A couple other things. What is the natural log of e equal to?
1.
Very good. Okay? Because there's an e right here, and e raised to what power equals e?
1.
1.
That's it.
Okay?
That's 11.
How about
I'm not good at Spanish.
the natural log of 1? What would that equal?
0.
0.
I did that
Good
one.
job.
I know.
Because e raised to what power equals 1?
0.
0.
0 to the 0.
Okay?
What is 0 to the 0?
I believe that is undefined.
That's 1.
I'm not going to get into it right now. I got a lot to get through. Okay? All right? Okay. Guys, we good?
Yep.
All right.
Locked and loaded.
Next thing. Y equals e to the x. That graph.
What was that?
Okay? Roughly looks
Oh, all wrong.
something like this.
It's exponential
It's
growth.
an exponential growth. It's really like y equals 2 raised to the x power, except it's y equals 2.7182, whatever, raised to the x power. Exponential growth. Okay? The inverse of e to the x power is the natural log of x. E and natural log are inverses of one another. Okay?
Oh, the graph.
So y equals the natural log of x. And that graph looks like this.
I only understand graph dances, so if you could please perform the graph dance.
Yeah.
Wait,
I failed dance class.
Did you?
You did dance class?
Hey, some linemen do it.
They do ballerina to keep their toes.
Okay, now,
Seriously. It is a lot, yeah. They do that,
real quick refresher on some other things. Y equals e to the x. What's the domain of this function?
Negative infinity.
Negative infinity to positive infinity. What is the range of this function? 0 to infinity. Okay?
And then it's flipped for the next one.
0 to infinity for domain.
0 to infinity for domain.
Negative infinity to positive.
Negative infinity to positive infinity for the range. They
Just
switch,
Just
right?
make sure to have the little parenthesis instead of the blocky thing because
Correct, when you're writing it in interval notation. Very good. All right. Now, we are going to do the derivatives of these. I'm not going to do a proof of these, but I'm going to logically talk you through why the derivative of these kind of works. All right? We will do proofs of some logarithm and other exponential ones later, but these two, you're just kind of going to take my brief explanation for based on the graph, and we're not really going to do a proof of them. The proof involves integrals, which we haven't done yet. As you'll see from the practice problems, they're like from chapter 5 in the book. Okay? But we're fitting them in now because we're still just doing derivatives. Okay? Let's talk about what a derivative means again. What do we do the derivative for? What are we trying to
the
find?
instantaneous slope.
Instantaneous slope, instantaneous rate of change, instantaneous velocity, you name it, okay? If I'm talking about the graphs, then we're talking about instantaneous slopes, okay? What would you say the slope is way over here to the left of this one?
Low positive.
Small positive. How about here?
Slightly
Bigger
higher
positive.
A little bigger positive. How about here?
A little bigger.
Bigger.
Okay.
A little bigger.
Very,
Very
big
big.
positive. Big positive.
Would you, if you had to graph the derivative, like remember those questions on those tests?
Yeah.
If you had to graph the derivative, what might your guess be?
Exactly the same as what
Exactly the
is there.
same. The derivative of e to the x is, believe it or not, e to the x.
They call me Johnny Cash for a reason.
They don't call me that.
They call me Johnny Cash. No, Johnny Cash. Straight money.
My favorite derivative requires you to do nothing.
I love that one actually.
Yep. Okay?
Can we do that one? We should only have
The
that.
derivative of e to the x is e to the x. Now, if you have to use the chain rule, which will be required sometimes, like if you have e to the 5x, the derivative of e to the 5x would be e to the 5x times 5. Because you got to take it times the derivative of what was up in the exponent. Okay? So, I guess I could also write then the derivative with respect to x of e to the u would equal e to the u times du or times du dx, how you ever want to write it. Just make sure you multiply by the derivative of what that exponent is, just like you always do in the chain rule. Let's do those two real quick.
Okay. You can write it down.
So then did you throw that like -3 out front then?
Just to clean it up.
Yeah.
Done.
Got one? You got the first one?
Yeah.
What would you do?
Well, you do e to the -3rd x times -3.
And where'd you get that times -3?
Well, it's the derivative of the exponent.
Very good. Okay. Let's clean it up. Good. Negative 3e to the negative 3x.
Why does the negative 3x not go down to like negative 4 or something?
The derivative of e to the x is always just e to the x. It's not changing. So, anytime e is your base, Carter, the derivative of e raised to any power is always going to start with e raised to that power. But if that power has a derivative, make sure you then take e to whatever it was times the derivative of that power.
Right.
So, but yep, it will not change. Okay. And the other reason, I guess, to maybe consider that is, keep in mind on our power rule ones, we had like x to the 5th, right? The exponent was locked in. You know, if we had x to the 5th, the exponent was just 5. Here, the exponent could be ever changing. So it wouldn't follow the power rule because the power is not a definite number. It's changing as x changes. Okay? All right. Amanda, you want to take this one?
Yeah, it's e raised to the x squared minus 6x times 2x minus 6. And then clean it up.
Okay. And then that one, yeah, you could put that first. Again, this one I can really see about either way. Since you really kind of have a quantity being multiplied. Now, if this was just 2x back here, then it would make sense for me to write 2x e to the x squared minus 6x. But honestly, on this one, since it's a quantity, I think both of those are fine. Sure. As far as how they look. Okay? Any questions on derivatives of e? Really, they're not too bad. Just adding another rule that you'll use within other rules, and you'll get practice with it. Okay? Y equals the natural log of x. I showed you the graph there. If we had to guess what the derivative or the instantaneous slope of this graph would look like, or the graph of the derivative would look like, where would I start?
Or no, that's a positive.
Large positive, right? My instantaneous slope right here is large positive. What's happening to it?
Getting smaller positives.
It's getting smaller positives. So you'd say it could start up here, and it's getting smaller positive, and what's it going to approach?
0. But it'll never reach 0.
So it'll look something like this, right?
Yeah.
Okay? What does that possibly look like?
Like half of 1 over x.
Radioactive
Part
decay.
of 1 over x. Okay?
Thanks, Carmen.
The derivative.
Only almost done.
What?
Okay? The derivative of the natural log of x is simply 1 over x. But only for x values greater than 0.
I'm trying to catch.
That was actually really impressive, John.
Yeah.
Thanks. Great job.
Okay?
Oh,
So again, this one's not bad at all either. Okay? Natural log of x is simply, the derivative of natural log of x is simply 1 over x. You want me to put the...
Do an example.
Now if you got to use the chain rule, you do 1 over u again times du dx. So you do 1 over whatever, and then multiply that by the derivative of what's inside.
Siri, not now. That's please not the only one.
Sorry.
Yeah, please.
Oh, you're making it hard.
Oh, but
You just hate it.
Hey, language, Betty.
I just said what the.
Oh, you were close.
You know what? Shut up.
Ooh, there it is.
Wow.
And there's the language.
Such a well-behaved class that everyone's proud of on
I'm glad
YouTube.
you're recording.
I want to know who actually watches these.
You have 50 subscribers though.
Wow.
Subscribers?
You have subscribers?
He just add some. Wait,
Wait,
you made 15
he
different
buys
accounts.
his subscribers.
different accounts. I bet Sam follows him. Subscribe to him.
Alright, hey, let's go.
Okay, tangent, that one's secant x.
Secant squared.
Secant squared x.
Yep. So what do we do?
ln.
What's the derivative?
1 over what's inside.
1 over what's inside?
Times secant squared x minus 3.
Nice job, Carter. Times secant squared x minus 3. Because the derivative of tangent x is secant squared x, and the derivative of negative 3x would be minus 3. And I just write that then as a simple fraction. Secant squared x minus 3 over tangent x minus 3x.
Very simple.
Ooh.
I tell you what, we're pretty smart.
Rush, if you say one more dumb thing, you're out of here.
Alright, come on guys. Hey, let's go.
I think we made it correct.
Oh.
Got the last one.
Oh. I thought we were. Yep, got it.
I got it. Don't worry.
Just wait, John. Got it.
Just simplify this.
Yeah, I did. Strike 3 batters.
What do you got?
2 over x.
How would we get there?
Oh,
1 over 3x squared
1 over 3x squared
times 6x.
times 6x. So that would be 6x over 3x squared, which would simplify to 2 over x.
Oh, big boy. Hey.
Okay? So, quick little example of derivatives of e and natural logarithms.
This guy's what?
yeah, you can.
Okay,
Hold on at them, though.
He is.
Out of the skill trade.
here is your homework.
So it's both of those
Thank you.
different.
Yeah, I think the first one's about natural logarithms and the second one's about e.
Ralph, win.
You don't have to do it like all the time.
I can't read it.